Space Telescope, the Messenger mission, some other missions, and currently he's working as a mission analyst for the New Horizons mission. So I'll let Mark go ahead and take it away from here.
All right. Thanks for coming, everybody. Did you have a good lunch?
I didn't even have lunch yet.
You have lunch? You ready for a nap? Yeah, okay, great, because that's what I'm here for. So, right, so I've been working on the New Horizons mission since about 2014, so right before it flew past Pluto. So I did not get to have all the fun involvement of planning for that part of it, but we are prepping right now, and have been since last year, to do a flyby of another object, a Kuiper Belt object, called MU69. It as yet does not have a nickname, but at some point NASA is going to release one. And the planning for this has been absolutely incredible. I'll probably touch on that a little bit, but at the end of the talk, I want to talk to you about MU69 and what we do know of it. So without further ado, New Horizons, our mission to Pluto. Our solar system, just to put everyone on the same page, is a very complex entity. It's composed of large objects from a giant star in the center of it. Well, it's not a giant star, it's a dwarf star, but it's larger than everything else, to some rocky worlds and gaseous worlds and a bunch of debris littered throughout. We've seen other star systems that have exoplanets. We've seen hundreds of star systems that have exoplanets, but none of those other star systems remotely resemble our solar system. So right now, with the knowledge base that we have, we are unique in the universe until we find other analog star systems. So for our solar system, we divide it into 3 zones. Zone 1 is the rocky world system. That's where Mercury, Venus, Earth, and Mars are located. It goes out to the asteroid belt. Zone 2 is where our gas giants are, Jupiter, Saturn, Uranus, and Neptune. And extends from the asteroid belt out to the orbit of Neptune, or the inner edge of the Kuiper Belt. The Kuiper Belt is basically where Zone 3 begins and extends outward. The Kuiper Belt itself is estimated to be about 30 to 50 astronomical units thick, where 1 astronomical unit is the mean distance from Earth to the Sun. So the thickness of that disk is about 30 to 50 times the distance of Earth to the Sun. And in that disk is littered millions of bits of debris of various sizes. Much of it is very, very small, but some of it is large enough that we can actually see from Earth. But since we've had, really prior to now, no spacecraft go out there and explore the Kuiper Belt system, the only information we have about it is what we can see from Earth, using either ground-based telescopes or really the Hubble Space Telescope. And it was Hubble images that really brought to light the fact that the Kuiper Belt even existed. Sorry. So, as I said, it's composed of millions of tiny bodies. It has a fairly extensive range, and all the short period comments that we get tend to come from this region of space. So what do we know about Pluto? We know Pluto is in the Kuiper Belt. It's part of the Kuiper Belt. It's in Zone 3. It's the first one that we discovered. It was discovered in 1930 by Clyde Tombaugh. He was charged by another astronomer named Lowell to look for Planet X, because they knew that there had to be something else out there. So he searched and searched and searched and searched and searched, and he found galaxies, he found star clusters, he found asteroids, and he found this other object that moved oddly and seemed to be very far away and faint. So he got his boss involved. They looked at it and said, it's out there past Neptune. It's really far out. So we have a new object, a new thing out in our solar system that had never been seen before. When astronomers went back and looked at previous data that they'd taken of the same part of the sky that Tombaugh found Pluto, they found they'd been imaging it a bunch of times over years before Tombaugh recognized what they found. No one just realized what they had gotten. When they did the orbital analysis of Pluto, they realized it's not like anything else in the solar system. It has a highly elliptical orbit. It has a highly inclined orbit. It looks more like a comet than a quote-unquote classical planet, but and it rotates very slowly on its axis, and it takes hundreds of years to go around the sun. We know that it's very far out there. If you were to ride a bicycle, it would take you a while to get there. Even if you took the shuttle, had it still be operating, it would take you 25 years to get out there. New Horizons was designed to get out to Pluto and explore it in a short amount of time as possible. And it took us still 9.5 years to get out there. When it was discovered, they didn't have a name for it. It was just an object. And it made the news wires, back then what they would have been the internet, and word spread like wildfire that the Americans found a new object out there. They didn't have a name for it, and this British guy in England was reading the newspaper to his family. His daughter, Venetia Burney, was having breakfast there, and Venetia was very, very versed in mythology. And he's reading to her about this new discovery the Americans had made. And they didn't have a name for it. And she goes, well, why don't they call it Pluto? After all, it fits in with the pantheon of the rest of the gods of the planets that are named. And Pluto is the god of the dark, the underworld, the dim, the invisible. And this object is dark, dim, and visible. No one had seen it before. It's so faint. So he thought, well, I'll send the suggestion in. And when Tom Ball got it, he got, I like it. That's fantastic. Not only does it fit in with the pantheon, but the first two letters are Percival Lowell's initials. And that's why that symbol is as it is. So what else do we know about Pluto? Well, up until 1990s, it was the only thing out there. After that, Hubble started picking up other objects further out, fainter ones generally, but it started detecting. We started finding what we call now the Kuiper Belt. Then they start finding larger objects, Haumea, Makemake, Sedna. They weren't as large as Pluto, but they were larger than the icy asteroids they'd been finding up to this point. Then they discovered Eris. And a big controversy came up, who's larger, Pluto or Eris? Pluto or Eris? Eris or Pluto? And various measurements were made, and estimates were within a few kilometers of each other. And then people started examining and going, well, what is a planet anyhow? No one really knew. The definition of planet is wandering star. That's the last time a formal definition had been made. That was a Greek definition. Up through the centuries, it was understood what a planet was. You looked at Mars, that's a planet. Yes, of course it's a planet. If you looked at Jupiter, well, yeah, that's a planet. If you looked at Juno or Vesta, no, those are not planets, those are asteroids. It's just intuitively obvious. But now we're at the Kuiper Belt. We're finding things like Juno and Vesta, icy asteroids out there that are smaller than Juno or Vesta. But now we're finding other objects, Makemake, Pluto, Eris, Haumea, Sedna, etc., that are large enough to be significant. And, well, the IAU had to weigh in on this, and through various politics that I'm not going to go into detail on, a certain astronomer who okay, I'll go into details on it. The IAU had a meeting, which they do periodically, and at the very end of the meeting, most of the planetary astronomers had gone home. So they convened the remaining astronomers who were there. Most of them were like stellar astronomers or galactic astronomers who have no clue about planets. And they said, well, we have a definition for planet, and we're going to propose it to you, and you're going to vote on it. Okay, fine. So they proposed a definition. And the astronomers go, okay, fine, whatever, and went home. And the background to this definition came from a British astronomer who took exception to the politics of a certain sitting president that we had in the United States at that time, 2006, you can figure it out from there. And he didn't like that president, so he was going to demote Pluto from planetary status, meaning that the Americans never found a planet ever in their existence, only Europeans. Politics, even in astronomy, there's politics. Okay? If you ignore the politics and you look at what the object is itself, you can reclassify it and not call it a demotion, which is what everyone's up in arms about. You call it a dwarf planet. It still has the word planet in it, doesn't it? The sun is a dwarf star. No one's up in arms about it being a dwarf. So for purposes of this talk, dwarf planets are just a subset of planets. Are we good with that? Yes, no, yes. Arguments, art? All right, so we have a whole subset of planets. We have the rocky worlds, we have the gas giants, we have the dwarf planets. All right, we have 3 subsets of planets in our solar system. Pluto itself. Pluto has 5 known companions. I stress the word companions here, not moons, when you count 5. Charon, also pronounced Sharon, was discovered in 1978. 2 more moons, Nix and Hydra, and notice I use the word moons here, were discovered in 2005. 1 more moon was discovered 2011, and another moon was discovered in 2012. New Horizons launched in 2005. So these 2 moons were discovered after New Horizons had launched. So we're still making discoveries from the ground about stuff around the Pluto system that we didn't know was there. Now the last 4 here, Nix, Hydra, Kerberos, and Styx, are very small. Styx is the smallest one. I think it's 9 or 10 kilometers across at the largest axis. Very tiny. Charon, on the other hand, is actually significantly larger. It's about half the size and 1/8 the mass of Pluto. To orbit a body, you have 2 gravity masses, and there's a center point. And if the center point is inside the other one of the bodies, then the other body is actually orbiting that larger body, because the barycenter is hosted within the confines of the main body. If the barycenter is between the 2, neither are orbiting each other, they're orbiting a point in space. And that's what's happening here with Charon. Charon and Pluto are massive enough to each other that the barycenter is 800 kilometers above the surface of Pluto, which means that's the point that they're orbiting, which means really Charon is a binary world Charon and Pluto is a binary world system in our solar system. This hasn't been formally ratified by the IAU or anybody, but if you look at how it works, that's what it is. Charon's not really a moon of Pluto. So Charon is a candidate dwarf planet. It has not been formally introduced as a dwarf planet. Now, to give you guys, most of you, I think, understand how faint Pluto is, but just to put numbers on it, the numbers here, if you're not familiar, which I think everyone is, these are magnitude numbers on how faint things are. Here's Pluto, far fainter than like 13.8 or anything. It's in the 14th magnitude range. Pretty faint, and especially for the early 1900s time frame to see. It's so faint, it's just a dot, and over a period of days, you can see it move across the background stars. So that's how you can identify it most easily. Now, can you identify it here? I'll get out of the way so you guys can see it. Can you even see the dots on here on the screen? I know it's bright.
Too much light.
All right, how about this one? Can you see that one?
Yeah.
Is that Pluto? Yes, no? No. How about this one?
No.
This one? That one? This one? This one? This was taken by the Cassini spacecraft at Saturn the day before we flew past it with New Horizons. Okay? So this is what the star field looked like then. And there's Pluto. Hard to see. Even from Saturn, it looks just like a dot. So from Earth, we have this thing called the Hubble Space Telescope. And you've seen amazing photos from the Hubble Space Telescope. Massive galaxies, spanning star clusters, colorful nebula, Pluto. I mean, this is an image of Pluto back in 1996. The best image we could get with Pluto. We could take it and put it into computers and deconvolve it, and we could see this. But this is pretty artificial. But we can see there's light and dark areas from the Hubble images. Okay, and we can see it rotate on its axis. So we could see these things change. When we got the advanced camera for surveys on the Hubble, you could see how it rotated. Now you guys have seen images of Pluto, and you know about the whole heart shaped part, right? There it is. We were already seeing it. So, but this is the best we can do from the ground, or orbit from Earth at all. We can't do any better. The only way we can is to go out and visit it, personally. So, New Horizons. This is the size of the spacecraft here, and a couple of folks at the APL were putting it together. It's not that large. It's the size of a baby grand piano. A funny side story, I was giving this talk to astronomy club in Asheville, North Carolina a couple years ago, and this room was packed with 150 people standing on the corners and everything, and I'm talking about the size of this. I'm saying it's the size of a baby grand piano. If you ever seen one, you can see it. And someone pointed in the corner, yeah, there's one right there. So you could go and stand next to it and see how big it is. Anyway, New Horizons was not the first proposed project or mission to go to Pluto. The first one was Pluto 350 by the Pluto Underground. This is a group of planetary scientists who said, we've been to Mercury, we've been to Venus, we've been to Mars, we've been to Jupiter, Saturn, Uranus, Neptune, we've not been to Pluto. We need to go. So they put together a proposal, Pluto 350. That didn't quite go. Pluto Mariner Mark II, then Pluto Fast Flyby, then Pluto Express, over and over. They kept proposing. And either the proposal would be accepted, but then the funding would dry up, or it just wouldn't be funded at all. Until finally 2001, New Horizons was accepted, the funding was there and didn't dry up, and we got our spacecraft. We built the thing in 4 years, and then we got it launched. Some trivia for you. The missions operations area is the Applied Physics Laboratory in Maryland. This is where I work. This is the mission operations room, but this is not where I work. I have a regular office that I sit in and do my work. There is a stamp on the spacecraft, a U.S. postage stamp that says Pluto not yet explored. Back in the day, the U.S. Post Office had put out a book of stamps for each of the planets and an image of each of the planets and Pluto not explored. So we put that stamp up there so we could say, yes, we did. Now, prior to Clyde Tombaugh's death, he was interviewed, and one of the questions that was asked was, if you could go anywhere in the world, where would you like to go? He says, I want to go to Pluto. That's my planet. So after he passed, Alan Stern, the gentleman whose picture was in the lower corner here earlier, he's our project scientist. He's the main guy, principal investigator who brought New Horizons together. He contacted Clyde Tombaugh's children, said, we'd like to have some of his ashes. We'll put it on a spacecraft and send it to Pluto. They said, do it. So there's a container of Clyde's ashes that bolted to the side of the spacecraft, and he's the first person to visit Pluto. So again, it's the size of a baby grand piano here in the clean room at APL. This black projection here is our radiothermal isotopic generator. That's our power source. We're so far out from the sun, solar panels won't work. You'd have to carry panels that are kilometers across to get enough energy to power this thing. And to give you an idea how much power this thing uses, the instruments on this only use watts of power, single-digit watts of power to do what we got to do. It carries 7 science instruments on board. It's one of the larger payloads that a spacecraft has had. And there's 2 solid-state recorders able to carry up to 2 gigabytes of data each, or 8 gigabytes of data each. Real quickly, the instruments, the LORRI is a long-range reconnaissance imager. It's our primary camera. The REX is a radio science experiment. Ralph and Alice are not acronyms. They were so named because someone on the mission liked the honeymooners. And then there's Pepsi, SDC, and SWAP. SWAP is the instrument that I work with that science team for doing their commanding. SDC I want to call out. This is the SDC team here. They're all college students. They were high school students when this was built. They designed and built and submitted this instrument to NASA to be put on the New Horizons. This is the only student designed and built instrument that's operating in space. And a number of these students went on to get their PhDs in the data that they've collected from their instrument. So New Horizons has a number of science objectives, a very, very ambitious mission. We're doing a flyby of Pluto, we're not doing an orbit. So we get one shot at doing anything at Pluto as we zoom by. And this is all the stuff that we want to do. Okay? I'm not going to read the whole thing, but imagine what you want to know about Pluto. We're trying to do it. We're trying to find out. So we built the spacecraft from 2001 to 2005. We built it, tested it, got it together. January 2006, we launched. 11 hours later, or 9 hours later, we flew past the moon. It took the Pioneers 11 hours to get past the moon. They were moving pretty quickly too. So we were the fastest launched spacecraft. We're not the fastest spacecraft in the solar system, but we're the fastest launched spacecraft. And a year later, 13 months later, we flew past Jupiter, which kicked some serious butt. You can see Pioneers took 20 months, almost 2 years. Voyagers took 1.5 to 2 years. New Horizons, 13 months. And then 2015, 9.5 years after launch, we did our flyby.
Was that because of orbital mechanics or because of the size of the rocket?
Both. To get to Jupiter's size of rocket, get to Pluto was orbital mechanics. I'll cover that in just a second, a little bit more detail. Just to give you a vague idea of how fast that is, someone at Google put this together a while ago, and I grabbed it. So this is what it looks like out of the 747, the SR-71 Blackbird, New Horizons. So when we went out, we flew past Jupiter, and we did that purposefully, the orbital mechanics part, to get a boost from Jupiter to get us out even further, faster, to Pluto. If we did not have Jupiter in the right position, and we had a very, very narrow window in which to launch to meet Jupiter to get to Pluto, it would have taken 5 more years to get to Pluto. We still wouldn't be there yet. I'd have to come back in 2 years and talk to you about what we found. But because we got to go to Pluto, or go to Jupiter, this is the track here, Jupiter right here, we got to see some cool stuff. We did exercising of the instruments. There was a flyby, so we might as well exercise the instruments, and we saw some things. This little fuzzy bit right here, this is the moon Io, and that's a volcano erupting, where the plume is a couple hundred kilometers above the surface of Io. We could see it. This is Ganymedes, Callisto, and Jupiter, and my personal favorite is this one here of Europa rising over the limb of Jupiter. It's just a pretty picture for me. I like it. You don't have to like it. I'll move on.
I want to hear 2001 music.
I don't have speakers hooked up. Planning for this is an enormous undertaking. The whole time we were flying out to Pluto, we were planning for the actual flyby. You know, we discovered Pluto in the 30s. We know how long it takes, not quite 250 years to go around. There's always uncertainties in how things are going. You have to, when you launch, you have to know where you are exactly, where Pluto is exactly, how fast you're going, where Pluto's going to move, how long it's going to take you to get there in order to intersect. And you want to make sure all the science instruments are going. We had a flyby box, if you will. If you were to say the planet's right here and we're coming this way, there's a small box that we're trying to shoot through. That's the ideal box where we want to fly through to look at the planet, be at a certain distance away from it, and have a very specific timing. We had to get the timing down to, plus or minus 30 seconds, 9.5 years out, to know where we're going to point the instruments as we flew by. And we had a 2-minute tolerance on the timing. We did it with 30 seconds. So there's a lot of other planning goes on. We plan for contingencies, and we still plan for contingencies. What happens if there's a computer reset? It takes 7.5 minutes for the computer to come back on. There's 2 computers on New Horizons. One is the primary computer that does all the operations. One is a backup computer in case something goes bad. If computer dies, backup one takes over. If we need to do changes in sequence, we have to radiate the sequences, the command sequences up to the spacecraft. We do them in bulk loads. So we do what we call command loads, are timelines that are 1, 2, or 3 week long command sequences. And this is just for the general cruise phase, where we tell the spacecraft, okay, you're going to use this instrument, you're going to do this at this time, and then you're going to change this filter, and then you're going to turn on this instrument, and then at this point you're going to turn back to Earth, and you're going to dump the data down, and then you're going to turn back away, and you're going to look at this, and so on and so forth. And we've been doing this constantly for, well, since launch. And we're still doing it today because the spacecraft's not idle while it's out there. It's still taking data. The Pepsi and SWAP instruments are basically what I call area effect instruments. They're plasma readers, and they're reading the solar wind as we're going out into the solar system and getting solar wind data as we go. So we're getting this beautiful map of how the solar wind acts over the time. Other planning we had to do dealt with, well, we were finding new objects orbiting Pluto. Holy crap! What if we hit one of these things? We didn't know these, like Styx and Kerberos, we didn't know they existed prior to launch. And what if our trajectory had us going through those orbits? Didn't, fortunately. So this red line, if you can see it, is the nominal trajectory that we had plotted out from before launch. All these other lines here are what we call Shabbat, safe haven by other trajectory. In case we found something that might be a danger to the spacecraft here, we could go to one of these other trajectories if we found it early enough, and we could then move the spacecraft over enough. And you see the angle that we're coming through on the plane of the Pluto system. Now this plane is actually tilted 90 degrees on towards the sun. So we did all these planning. There was a team of engineers who were tasked with coming up with problems and then saying, what we had were all these scenarios. They had to come up with scenarios that the rest of the New Horizons team had to solve on the fly immediately. Such as, well, you just had a spacecraft, you just lost one of the instruments. For some reason, it stopped working. It's now in safe mode. Safe mode is a level that the instruments or the spacecraft goes into when there's a problem, and it can power down to a mode where we can still communicate with it, talk to it. What do? The team that came up with these came up with many hundreds of very evil scenarios. And they would just randomly send the scenario out to the team. This just happened. The team had to drop whatever they're doing real time. If they were working on another mission, they had to drop it and fix the problem and come up with a solution. And it's stressful. But the team who came up with the scenarios had lots of fun with it. We didn't get through all of them. There's just so much you can do in the time allotted. And it takes time to solve the scenarios and everything. And also we have the whole round trip light time. As New Horizons is going out, the further it goes out, the longer it takes a signal to reach it, and the longer it takes a signal to come back. What we call an RTLT, a round trip light time. Okay? So we had all these scenarios. We didn't get to all of them. Then, right before the flyby, July 4th weekend, something actually happened on the spacecraft. And it was a bit of a stressful time. It turned out to be exactly one of the scenarios that we didn't get to practice. So we got to do it in real life. It took the weekend to get the spacecraft back online and back running properly again. But what had happened was, how many of you are familiar with the blue screen of death on PCs? Yeah, that's what happened. The main computer had the blue screen of death. It was trying to do too much, and it said, I can't do this, I'm shutting down. The backup computer said, hey, look at that. The main computer just shut down. I'm going to save the spacecraft. Because the main computer couldn't do it. So the flight operations crew, the people who were monitoring, all right.
Just been saved.
I've been saved. I've been recovered now. The woman, friend of mine who was monitoring what's going on. She was working on an email to somebody, I don't know who, what she was doing. She said she was typing away. She looked over at the monitor screen where she was monitoring the telemetry that was coming down from the spacecraft. It's just a basic telemetry stream. And periodically it would go gray because you have a telemetry dropout, but a couple seconds later it'll pop back up and be all green. You get all these green numbers and everything's fine. She looked over, okay, it's gray, fine. It's gray. It's still gray. It's still gray. This is bad. 10 seconds have gone by. At this point, it's panic mode because we no longer have communication with the spacecraft, inexplicably. We should have an 8-hour block of time with the spacecraft, and now we have nothing. So she sent out another set of emails to the upper engineering teams for the spacecraft and the management, and one of the guys happened to be in the area when he got the email, so he drove in and he walked in the room and said, "How long ago did you lose communication?" And she told him the time. She goes, "All right, let's wait till this time, which would be 90 minutes, and see if we get a beep. If you get a signal, it's just a beep, like a homing beep, we know the spacecraft's alive. If not, well, there may be something else wrong." So they waited. 90 minutes after she lost telemetry, they got the signal. The spacecraft was alive. Now, they had to spend the rest of the weekend figuring out what went wrong and how to recover it. And as they went through the scenario, they realized this is one of the scenarios they never practiced. The round-trip light time was about 11 hours. Just send the signal out. It's 11 hours before you get a response back. It took 3 RT-LTs to get the spacecraft back up and running. And in that time, we didn't lose any critical science. We weren't in the flyby sequence just yet. We were days away from the flyby sequence. We did lose some planned observations of Pluto, approach observations, but they weren't critical. We could take them or not. They would have been nice to have, but we got through it. July 4th was the safing event. The encounter sequence began July 7th. We had the spacecraft back operating on July 6th.
By the skin of your teeth.
Skin of the teeth, yeah. I was out in Western Maryland at the time, rock climbing. Where I was, I had no service on my cell phone, so I didn't even know anything was wrong. Got home, I got a call, I got a text message from the SWAP instrument scientist saying, "Are you in the MOC, the Mission Operations Center?" I'm going, "It's Saturday, why would I be in the MOC?" I didn't hear anything from her, and she's like that. She'll say something and then you never hear from her again. So I thought, okay, fine, I'm going to log in. And I find all these emails going, for the last 4 hours, something's been going on. So I called in and I talked to one of my colleagues there and said, "Hey, do you need me in? What can I do?" She said, "Best thing to do is stay home and be on call. We have a bunch of people here right now, but if we need you, we need to know where to find you." So the rest of the weekend, I sat there on the couch, watched the beautiful day go by, waiting for the call that never came, which is fine. I didn't mind. I'd rather that happen than they had to also call me in, because of all the people who were there, they had more knowledge of how to deal with the spacecraft recovery than I did. So we got through it. Oh, I want to go back one. So we did the flyby on July 14th, and this is the orientation where we went. This is where the different moons and companion Charon was relative to when we did the flyby. Then we had this thing back here called a phone home. It happened that night. So while the spacecraft is doing its thing at Pluto, it can't turn the antenna, which is fixed to the side of the spacecraft, and face Earth and communicate with it, because that takes all the instruments away from looking at Pluto, Charon, and the rest of the system. So the only thing we had basically was a little signal that said, "I'm alive." That's all we had the whole time. Until we got out here, when we got the spacecraft to turn to us and say, "Okay, I'm really alive, and everything's good." So we were much happier at that point, and then the next year we downloaded the data from the flyby. On approach, you can see here's Pluto and here's Charon orbiting the Berry Center right here. This is taken about a couple months out from closest approach. By June of 2014, we were doing better than what the Hubble could see on Pluto. Much higher resolution than what the Hubble could do. And the Hubble images you saw were all deconvolved. This is straight raw. And then just a few days out from closest approach, we saw Pluto. I mean, we saw Pluto. And there's the heart-shaped region right there. You know, we verified that this is a real thing, not just some weird odd object that was being picked up by Hubble. This is the other side of Pluto. You see there's a bullseye here, bullseye here. These are probably craters. Another day in, looking more modeled, more detail. What was cool, I'm not in the science team, I'm in the mission operations team. So I'm busy putting the command sequences together for the scientists. They tell us what they want, we deconvolve it, we send it up to the spacecraft. But I have a science background, so I get to go sit with the scientists periodically and hang out with them and just learn what they're doing. So it was cool to sit in with them every morning when they were getting the latest data down. And they get down, like, they get this first data image down. They go, oh, look at this. And then you'd have 50 people crowded around the screen pointing and going all bananas over this image of stuff we'd never seen before. The next day, they'd forget about it because they'd see that one. And the next day, they'd forget about that because then they see this one. And it was just thrilling to sit there and watch them just go nuts over this. And it was cool to see also. I couldn't talk about it at that time because it was embargoed. They have to release the data before I could talk about it. But it was cool to see all this stuff. And then we had the flyby image. So in order to have an intelligent conversation about what you're talking about on the surface of Pluto, it helps to name things. Rather than say that dark area to the left of the light area just past the bluish area below the bullseye crater. Instead, you could call it the Cthulhu ratio, or the Venera Terra, or the Tomball ratio, or the Sputnik Planum. Give them names. These names were unofficial when they gave them. It was recognized. It has to always be called out that these are unofficial names because the IAU is the body that names features. And their naming scheme is for underworld mythology from various mythologies, gods, goddesses, dwarfs associated with the underworld, heroes, other explorers of the underworld, and writers that are associated with Pluto and the Kuiper Belt.
Since we sent New Horizons America to, we should name them after U.S. presidents.
That would be good.
Back at the Europeans.
So a couple months ago, this came through. These names specifically are official on Pluto. And a couple of them are dear to my heart, like Tenzing Montes and Hilary Montes are named for Sir Edmund Hillary and Tenzing Norgay, the first climbers to successfully climb up and get back down alive of Mount Everest. And when I saw that they were unofficial names, I was like, please, 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 this would be so cool to have some mountaineers named there. Not only that, but Tenzing name, if they kept his name, and they did, his is the first Nepalese name on any object in the solar system. So that's cool too. Burney crater is after Venetia Burney, the young lady who named Pluto. Elliot is a, crap, I can't remember his role in things. Tartarus Dorsa is the deepest, darkest pit of hell. Tomball Regios, named after Tomball. Sputnik Planitia is named after the spacecraft Sputnik. The Voyager Terra after the Voyager spacecrafts, and so on. This is a perspective view of the Sputnik planum right here. Basically, you can think of it as a giant nitrogen glacier. It's got all the hallmarks of it. Just looking at it here, the Hillary and Tenzing Montes are right here. This is the edge of it here. Can you guys see a slight discoloration in this right here? This might be a little bit better. Do you see how it's broken up like ice sheets? And when they looked at it better, you can see there's actual flow patterns in this area here, around all these polygonal cells. And then this is the highlands up in here. And you got flows coming down onto the sheet. You have flows here, coming here, and so this is looking at it with the sun at a certain angle, then this is looking at it from a different angle, and you can see the ice flow, the nitrogen ice flow here, forming this bubble, coming off these highlands over here. And here, now again, the rugged highlands over here, you got this hummocky terrain, you got all these pits in the flat plains areas. They're still working on these, but they're measuring some of these pits are 1 or more 100 meters deep. And you've got these clusters of hills that seem to appear around the edges of the polygonal cells that make up the Sputnik planum. And what they think might be happening, or at least one theory of what's happening, is these cells are actually convection cells, where the nitrogen ice is bubbling up and is sloughing off onto the edges. And these hills are actually water ice. Gobs, giant, like hundreds of meters large gobs of water ice that have bubbled up and are just floating out there on the nitrogen ice shelf. Here you can see the polygonal terrains better. You can see these dark spots here.
Mark,
Yeah.
the light from the sun there, when you take these images, I imagine these images must be a few seconds long.
Yeah, okay. How bright is it on Pluto? 5 minutes after the sun sets tonight. That's how bright it is.
How bright it is.
So it's not actually super dim.
Okay.
It's dim, but if you go out tonight, 5 minutes after the sun sets, that's as bright as at noon on Pluto. The Montes down here, these Montes, these are water ice mountains 11,000 feet tall. Pure water ice. Just solid as a rock. Ice climbers would have a hard time climbing because the ice is so dense, you can't get their crampons or ice axes into it. They would just bounce off or break. Not to say it's also cold, but it's cold enough out here that this stuff is solid. It's fine. You have an infill crater here where the nitrogen ice flow has come in, and you have the polygons here. The Norgay Mountains are here. Hillary Mountains here. There's another view of the Tenzing Mountains here. Then you have this depression right here. This depression is one of 2 cryovolcanoes that we've found. This is one, and the second one is down here outside of this view. And you can tell this one here, the crater is this right here. This dark area is this right here. There's a crater right here that's right here. Then this dark area is this here. And that makes this thing down here. They weren't active when we went by. We don't know when they're active, but they have all the hallmarks of a volcano, except it's too cold for lava. It has to be a nitrogen volcano, which is basically a cryovolcano. Another view of the other mountains that we found, these ice mountains that we saw. A close-up, and you can see some detail in the polygonal terrain, these ridges or rills that cross it. One of your things are...
It's going to stop.
Okay.
Can't hear it.
In addition, looking over here in the dark region of Pluto, we have these light areas. This is methane snow on top of these mountains in the dark areas. And this purple here is a filtered image which verified that's methane snow that we're looking at. Again, you can see the mountains here and the white caps on top of them, and then the more plain area here that doesn't have the snow. Water ice. The blue areas are where we've detected water ice on Pluto. Pluto is basically a giant water ice ball with a lot of impurities in it. And you see the Sputnik planum is right here, is not water ice, it's nitrogen ice. Off to the side, where we see a bunch of bullseye craters here, the bullseye, the blue, is water ice, the purple is methane. So all these craters are basically ringed by methane and have views into the depths of Pluto, the bottom of the crater, which is water ice. And craters in general, this tells us that the Sputnik Planum is a dynamic environment on Pluto. We have craters all over here that we've counted. This is as of 2015. I don't know if they've identified any more since then. There are none on the Sputnik Planum at all, which tells you that this thing is actually evolving, boiling as fast as it boils at this temperature, and changing. It's constantly changing. So if something impacts here, within a few hundred years, the impact crater's gone. It's been subsumed by the action going on the Sputnik Planum. And there's just so much. I could spend 3 hours talking about Pluto. I really could. But we don't have 3 hours because you guys want to go eat dinner or observe or something. So I'm going to move on to the next topic, which is the atmosphere of Pluto. Pluto has an atmosphere. It's not very thick, but it's there. And it's in layers. This is not a JPEG artifact. These are actual layers of the atmosphere. Again, these are layers of the atmosphere. This is the Montes, this is the Tenzing Montes and the Hillary Montes here. You see the atmosphere extends up quite far. It's hundreds of kilometers up. Another view of the Montes and the layers. And because Pluto has an atmosphere, albeit thin, there's light scatter. And because we have light scatter, we can look past the terminator into the night side, stretch it, and we can see some of the night side from light scatter. This is the twilight area on Pluto. How cool is that? Not very cool? All right, well, I'll go to the next one. So again, some more atmosphere, some more backscatter here. And here, you can see the actual profile of the edge of Pluto. It's not a smooth ball. It's got features on it. Another thing we did when we measured the atmosphere was we had plotted and planned. Again, think 9.5 years earlier we planned to do this before Pluto got to where it was, before we got to it, to fly behind Pluto and do a study of the atmosphere that may or may not be at Pluto. We didn't know. So we were going to fly past it, and this is the signal we got of this. We saw the sun dim, and then it dimmed more, and then as we got to the edge of Pluto, it disappeared. The sun went behind Pluto, it's gone. And as soon as the sun came back out, and it rose and it got brighter. It didn't go instant. We did the same thing with Charon. Again, we planned this 9.5 years ahead of time. The sun, we went behind Charon, came back out from Charon, the sun. There's no atmosphere on Pluto. On Charon, I mean. So let's see a movie. Okay, because I want to stop talking for 30 seconds. This is the flyby coming in. You'll see the moons and Charon orbiting about with Pluto. We'll zoom in, we'll slow down, we'll pan past Pluto. As we pull away, you'll see the backside of Pluto. You'll see the sun come up from outside the point of view of the camera. Disappear behind Pluto. You see it ringed by the atmosphere. Pop back out again. Then it'll blink when it goes behind Charon. Now that I've told you everything, I can skip the movie, right?
No.
Hello. There.
Wow.
You guys want to see it again?
That was the actual.
That's the footage that one of the science guys put together from all the stuff that we had. How was sitting behind him when he was working on this. I was like, what is he doing? What is he doing? And then I realized what he was putting together. And I said, I want to copy that when you're done. All right, so you guys are done with Pluto now? Shall we move on, please? I mean, really? How about Charon? Let's give Charon a little loving here. Charon had been actually observed for years without anyone realizing it. Again, like Pluto, the astronomers who were looking at Pluto and studying it with ground-based telescopes kept seeing this bump appear. They said, oh, look, an instrument feature. Throw that data set away. This is what we're looking at. They kept looking, they kept, oh, look, that instrument feature appeared again. Throw that data set away. And they kept doing this. Then, gentleman right here, whose name I'm now spacing, he was looking at it and he saw this bump appear regularly, like every 6.5 days it would appear. It's like, this is not an instrument feature. There's something there that's happening. So he went to his supervisor and they looked at it and said, you know, we think we have a real object. This could be a moon if it's not a contact binary of Pluto. So they studied it more, and then through various occultation studies and things, they figured out, oh yes, it's actually, there's a moon there. And better telescopes were able to eventually resolve the two as individual objects. This is our approach a month out of what a New Horizons saw of Charon. This is a deconvolved image, and we see there's a dark patch here. This light patch is just an artifact. But we can see there's differentiation. And then during the closest approach, this is what we got. There's our dark patch up here, and there's all these features here. You got this giant ridge line that seems to cut lengthwise across the body of the world. You have a plains area here full of craters. You have a higher plains area here, not quite as full of craters. The reddish area is reddish from tholins that we've determined have come from Pluto. And here are the names that are being used to identify features on Charon. They are still unofficial names. They have not been ratified as official. But to give you an idea where some of these come from, you have Alice Crater for Alice in Wonderland. You have Spock Crater for Spock. Mordor. Leia Crater, TARDIS for you Doctor Who fans. The TARDIS Chasma. The Gallifrey Macula, another Doctor Who reference. Macross for you Japanese anime fans. Nemo for Nemo Crater, and so on and so forth. You get the theme here of where they went with the naming convention. This is just a look at the bisection here of this part of the planet right here. You can see this giant cliff line that bisects the area right here. And in the plains here, what you don't see so much here, are all these fossae, these depressions or canyons. Again, this is along the ridgeline here, and this here is an avalanche slump. There's an avalanche slump right here. There's an avalanche slump right here, and there's one right here. That, who knows how long ago they happened. Off in the corner of Charon, we saw there's a canyon. We're only seeing the edge of it. But it goes from here, cuts through this dark area here, and it disappears over here. Hundreds of miles long. We don't know how deep it is. And then this is a view of Charon backlit by Pluto. Okay, are we done with Charon now? Can we move on? Let's give the other bodies a little bit of loving. What little there is. Styx, Nix, Kerberos, and Hydra compared to Charon in size. Tiny, tiny, tiny things. Again, Styx is the smallest one. It's 9-10 kilometers across. Nix and Hydra are about 30-40 kilometers across or so. Here's one of the early images that we had of Hydra. You see it wasn't very nice. So one of the instrument scientists ran through a deconvolution program and they found G.I. Joe. But this is what Nix looks like. This is the best image we have of Nix. They're blurry, they're small. We we only had so much time to plan to look at this, that, and the other, and we tried doing as much as we could. But you can see there's a big depression here, there's some craters here, there's a depression here, there's other depressions. And Kerberos and Hydra, Hydra and Styx look very, very similar. Kerberos is a bit smaller, we have less data, and Styx is just a blurry thing. But when we took spectra of these, compared it to ice, white is a pure ice spectra, Charon, Hydra, and Styx. You see they're nearly pure ice, covered with impurities, just dust or something. Styx is the most like an ice, a true pure ice, water ice ball. And again, this is enhanced color on Styx. This is Hydra here. You can see there's a big depression here, another depression here. That's Styx. That's it. That's all we got. Until we send another spacecraft up there, that's all we're going to get. Now it took from July of 2015 to October of 2016 to get all the data down just from that one day's flyby of the Pluto-Charon system. So that didn't mean we were done. The mandate for New Horizons was to explore Pluto and the Kuiper belt. The idea was, after we explore Pluto, after we get past that, to see if there's anything else out there on a trajectory that we can get the spacecraft to and go fly past it. We used ground-based telescopes for several years, looking at a cone where we could send New Horizons to, and found nothing. There's nothing out there, empty space. They finally called in the Hubble Space Telescope, and they had a blip. They said, we're going for it. They actually had two blips, and they had to decide. It was one or the other, and they chose target number one. So, January 1st, next year, at 12:30 in the morning, we will be flying past our new object, the artist rendition here. We don't know much about it. We discovered it with the Hubble, using many orbits of Hubble time to look at this thing. It's just a fuzzy dot. There's nothing much that we can tell. We can see there's variance in the brightness, so we know it's rotating, but we didn't know much more than that. And you see it right here. That's it. That's all Hubble got. We have more visits planned this year with the Hubble to get more data from it. But we were able to determine that there seems to be a period of about 5.5 hours on the variance of brightness. Whether that's rotating or something else, we're still trying to figure it out. Again, we encounter it on January 1st. Happy New Year. But to get more data, how many of you are familiar with occultation studies? A fair number of you. Okay, for those who are not, to do an occultation study, there's a group called IOTA, International Occultation Timing Association, who study when asteroids pass in front of a star. And they set up, they figure out where the shadow line is going to be, where the asteroid's going to pass in front of the star, and they set up a string of telescopes perpendicular to that shadow line and try and catch when it will be occulted. And from this data, they can trace the shape of the asteroid. And they get some timing information and things like that. So this particular asteroid here looks like that. You can see the shape just from where the timing of the occultation was. We also have a spacecraft, or not spacecraft, an aircraft called Sophia that does flies up in the atmosphere and does studies there. So we get above most of the clouds, get away from the lower vapor. We can go do studies over areas where, like the Pacific Ocean, where there's no easy way to set up 20 telescopes over a 100-mile stretch. You can fly the Sophia through an occultation thing. So we were using occultations of MU-69 to try and figure out what the shape of this thing is, how big it is. We had 3 opportunities last year, one in June and then 2 in July. One of them was over the Pacific Ocean, so we had to use the Sophia aircraft. The other 2 was Argentina and South Africa, and then again Argentina and Chile. We took a number of attempts. The first attempt in June missed completely, which is not a total failure. It just refines the orbit to say it's not here, it's actually someplace else. So Sophia had found it here, and then but the second July one found it right here. And it's really hard to see from there, I'm sure, but you can see it blinking right here as this is a star, and MU69 goes in front of the star. You can't see MU69, it's so faint. But what the planetary scientists have finally deduced, originally they thought this might be a moon. They're now saying it's not a moon. I don't remember what the explanation of that is, but they're suggesting that MU69 is actually either a contact binary, there's two objects that are right next, they're contact and orbiting each other, or it's a bilobal object because of how the shape is that you can't see because it's too dim in this room. But there's a lobe here, and then there's another lobe over here. And that's all the data we got. We'll find out in a little less than a year what it really is. We are here right now. MU69 is right there. January we will be there. The encounter phase, again, a close approach at 0533 UTC, which is 12:33 Eastern Standard Time. Our RTLT will be 12 hours and 16 minutes. So it's going to be a while before we get a signal back from the spacecraft saying that, oh, I'm still alive and here's the data. The first images we expect to get from New Horizons will be this September. We'll be imaging. We're imaging now, but we don't expect to actually pick up anything with the cameras until September. We'll be, at this point in time, we'll be about 3 times closer to MU69 than we were Pluto, or about 3,500 kilometers away from the object. We're hoping, if we get that close, that we'll have a resolution of about, well, not much larger than this building, and we will have another spacecraft first. It's the furthest flyby that any spacecraft has done in history. So start doing the optical navigation images, where we're taking images in high resolution to see if there's anything else out there we need to avoid. And then we have close approach. We then go into solar conjunction, like days later. Pluto goes behind, or MU69 goes behind the sun. We lose all contact with the spacecraft for a few days. And then after that, we start downloading all the data that we got. And it's the website if you are interested in following along. This is the primary one here. Just got to do Pluto, jhuapl.edu, and it will have the latest, greatest news releases and or images that we have. Thank you. Oh, one other thing. This is our new logo. That's Pluto up there, and the border is the surface of Pluto. That just came out last month. So, thank you again.
What's after that? Has anybody thought about?
Oh, we've thought about it. We haven't found anything yet. Right, the idea is to keep looking at, if we find something, we'll try. That's our mandate until we run out of energy. The RTG has enough plutonium on board to power the spacecraft and instruments until the early 2030s. After that, well, we're done.
Well, quite a while.
It's a bit, but it'll come quick.
Yeah, quick.
Yes.
All that program to do with all those cameras and that isn't flying by. Because it has to be
Yeah, we have to pre-plan everything.
planned everything.
On bottom.
Yeah, we do simulation after simulation after simulation to try and get it right and fit it in.
Do you have any data on the rocky surface of Pluto?
And what it's composed of, I don't personally know what it is off the top of my head. Yeah.
First question, so it sounds like you just go from mission to mission?
Well,
Around the JPL world, or for you?
No, I've actually been very static compared to a lot of people in the space mission world. When I first got to Hubble, I was told you don't stay at a mission more than 5 years. And I was on Hubble for 17 until I won the lottery and moved on due to budget cuts. But that allowed me an avenue into Messenger. I stayed on Messenger until it ended in 2015. I was about an 8-month overlap between Messenger and New Horizons for me because our group supervisor, and both missions are at APL, she wanted to have people transitioning from Messenger onto New Horizons, so she started moving me on a year early. So I would be cross-trained when Messenger ended, I could just jump right in. So I haven't bounced near as much as a lot of people I know. Right? Well, thank you, everybody.
Is that the new telescope they're working on, the infrared one?
Oh, the James Webb telescope?
Is that going to go up this year?
We hope.
Yeah, I just wondered.
Yeah. I'm not involved in it, so that's the people who do the Hubble are involved in it.
You guys did your stuff for 4 years, and they've been working on that for a while.
I know.